Hi and welcome to this video about drivers and devices. That's going to be a first part out of a two-part series about drivers and devices. So let's get started. What I want to talk about in this video is about the term kernel driver and a device object, which sometimes are used interchangeably, but this is not really right. So let's see what are the differences and how they are both represented within the Windows system. So first, the kernel driver term represents some kind of behavior. So you can think of the driver as like a code, just the code behind that manages certain behavior on behalf of actual devices, which could be physical devices or virtual devices. So there's one driver that can take care of multiple devices. For example, if I have a keyboard connected to my machine, maybe my laptop keyboard, there's a driver that's handling that. If I connect another such keyboard or a different keyboard, I might have the same driver taking care of both of these keyboards. And so a driver can be handling multiple devices. Sometimes there's just one, sometimes there are more. And sometimes the devices are dynamic in the sense that if I plug out my keyboard device, then some device object will have to be destroyed. If I plug in a new device, then a device object from a software perspective needs to be created. From a driver perspective, the driver object itself is a data structure that is actually fully documented, or at least almost fully documented. It's created by the kernel and provided to a typical driver using the driver entry function, which is like the main function of a driver. Device objects, on the other hand, and I mean that from a software perspective, are created on demand by drivers as new devices they need to take care of appear in the system. So this appearance is mostly because of plug and play, but I'm also referring here to virtual devices, which can be created manually. Regardless, the way Windows works is that the communication endpoint is a device. It's never a driver. We open handles to devices, never to drivers. For example, suppose you have 4 serial ports in your system. Now I know serial ports are very rare these days, but let's just assume we have 4 serial ports on that kind of system. In this case, we'll have a single driver that's going to represent the behavior and functionality of how serial ports work, but then in terms of devices, we'll have to create 4 device objects. Each one has its own name, each one is connected to its own hardware resources, such as an interrupt port or some I/O port, and so on. So every device is really a communication endpoint. We always open handles to devices, never to drivers. Device object created manually by drivers as needed, whereas a driver object is created by the kernel to represent the existence of the driver. And devices represent physical or virtual devices. So a device object could represent your network card, for example, but could also represent some virtual device, like the device created by the Process Explorer driver when it's running with admin privileges. Devices can also be layered. So you can have multiple layers of devices. In fact, this is very common, especially when dealing with hardware devices. Drivers cannot be layered technically. So sometimes people say that drivers are layered. What they really mean is that devices created by these drivers are the ones that are layered. Drivers are just on the side, so to speak. They're just providing the functionality and behavior. So here's one way of looking at how a driver and a bunch of devices are connected. And we'll be able to see that in the kernel debugger in a couple of minutes. So we have a driver object represented by the driver_object structure created by the kernel for us. It is partially filled in by the kernel and then passed to driver entry, the main function of the driver, to further customize the behavior of the driver, which essentially means sort of publishing and telling the kernel what this driver is supporting, such as read, write, device side control, things like that. We'll discuss that in the second part of this two-part series. So the driver object points to the first device object being created using a member called device object, and device object itself is another data structure called device_object, which is created by the appropriate driver when needed. And there's some details there which are a bit out of scope for what we're trying to do here. And then since there could be multiple devices, there's a next device member there that can point to the next device. In any case, there's a driver object pointer that points back to the driver object, which is sometimes convenient because in a driver, sometimes you get some kind of callback with the device object pointer. And if you need to get to the driver object, you can always do that using the driver object back pointer. Looking at the next device, there's another one, then the next device member points to the next one and so on. So in simple cases, there will be just one device, but in more complex cases, there might be multiple devices, and so on. So we have this next device member that points to the next device. There's always the driver object pointer pointing back to the driver object, and the last device is going to point to null, indicating the end of this list. This is just a single linked list, a special one that is used here to manage device objects that are part of the same driver object. Let's see what we can find out using some tools. So first, let me run WinObj from sysinternals. So WinObj is a tool that allows us to look at various named Windows objects, and drivers and devices happen to be named objects, especially drivers. Devices don't have to be named, although they are usually named, but they don't have to be in technical terms, and I'll explain perhaps in the next video why. So first, there's a directory here that's called driver. Now remember, these directories are in memory. They're part of the Object Manager namespace. And you can see it seems to be empty. This is just because we don't have enough permissions to view these directories. So I'll need to rerun WinObj with admin privileges. I'm going to relaunch that with admin privileges. So here goes. Now that we are running with admin privileges, going to the driver directory does show something. So these are all the driver objects currently loaded into my system. They each have a unique name and they're stored in this driver directory. So you can see something like the beep driver here, for instance. Or if I launch Process Explorer just for fun, I'm going to launch that on my other screen. And we expect to find the Process Explorer driver here. And here it goes, here it is. It's called ProcEXP 51152, which is the version of the Process Explorer driver. So many drivers exist here, mostly in this directory. Not all of them are actually here, but most of them are stored here, at least as a matter of convention. There's another directory here called device. This is where you find most of the named devices in the system. Some seem to have very silly names, like the 00011 or 0025. It seems to be something that doesn't really make a lot of sense, or perhaps doesn't provide lots of insight into what this device is all about. And there's actually a reason for that, which I'll discuss, maybe in this video, maybe in the next. For Process Explorer, for example, there's a device called ProcEXP 152. This is a communication endpoint used by Process Explorer to talk to its device, which will then, based on the behavior of the driver, do something useful for Process Explorer. Another example is the beep device. That's the one that does, well, beeps on your system. And there's a device that is the communication endpoint where you can open a handle to this kind of entity, if you so desire. The fact that the driver's name is also beep doesn't really mean anything. So these names need not be the same. In this case, they are the same because it makes sense, since in the case of beep, there's only one device that has the name beep. There's just one device that is managed by the beep driver, and so it has this simple name like beep. But in other cases, especially in plug-and-play cases, it doesn't have to be like that. If you double-click any of these device objects, you might find some details about those device objects, perhaps not very useful, but still something to look at. In terms of handles, in this case there's 0, and some aspect related to security. So that's fine, at least for now. Let's go ahead now and take a look at the kernel debugger. So in the kernel debugger, there's this command called drvobj, or drvobj, that's the real command name, where you can pass either a pointer to a driver object, if you have its address, or a name of the driver object, such as beep. And the command is smart enough to look in the driver directory automatically. Then you can specify a bunch of flags indicating how much information you would like to get. I'm going to use the value f to receive as much information as I possibly can using this command. Now before I do that, let me just break it here. Let me try to break. I'm going to use .reload here to force some kernel symbols to be loaded, so we have some nicer information to look at, and then I'm going to invoke the drvobj command again. This is a local kernel debugging session, but you can do that, of course, in a remote kernel debugging session in exactly the same way, naturally. So this command is a fairly slow one, so it might take a few seconds. I'm going to pause this recording until we get a result. Okay, we get some output from drvobj command. Let's scroll up. So you can see here we have this driver object. It has the name beep perhaps, but this is the actual address of the driver object in memory. And the full path in the object manager namespace is driver beep, which in fact we can verify by looking at winobj. That's exactly driver beep, what we expect for this driver object. That's the full path of the driver object for the beep device. And we can see here there's a single device here. There's just one of these devices, that's it. And then we see some information about what this driver supports. So you can see here we have the entry for the driver. There's also something called start.io and unload routine, which I won't be discussing right now. And then we can see an array of something called major function codes. And this array of major function codes, this is just an array of function pointers that indicate to the kernel what operations this particular driver supports. So you can see here that the beep driver supports the open operation, which is actually the create operation, and the name of the function happens to be beep open, and the information here is provided by the public symbols. It also supports irpmj close, which is the opposite operation of open. There's a function called beep close for that. And by the way, irpmj create is what is being invoked when you use the create file function from user mode, as we'll see in the second part of this video series. And irpmj close is actually for close handle. And then we have lots of these entries you find here called io-pinned valid device request. This is an internal kernel function that completes the request with a failure status indicating that this particular kind of operation is not supported. So for the beep driver, it supports create, it supports close, but it doesn't support, for example, read or write. It doesn't support these operations. What it does support, however, is device control. That's a device side control API from user mode, for example. It also supports another operation called cleanup. So it doesn't support a lot of operations, which is kind of understandable since this is a beep device, not a very complex device. This function, by the way, is the value that is being used as initialization for all this array. And the purpose of the driver and driver entry, one of the things it needs to do is to overwrite these pointers only for the operation it actually supports. If you want to see what happens in this particular function, you can just go ahead and dereference that or disassemble that, to be more precise. So we have this assembly here for the function io-pinned valid device request. So UF is an unassembled for a full function. And you can see here something, well, even if you're not an expert in assembly, you'll be able to see the basic idea here, which is to complete a request with the status being this value. And this is the value indicating that the operation is not supported. How can we tell for sure? I can go ahead and grab this value and give it to the error command, and the error command will provide the string description of that empty status. You can see it says the specified request is not valid operation for the target device, essentially meaning that this is not supported. So if I try to ask the device, if I open a proper handle to it, and I ask the device, please give me something using read or write, I'll get immediately a response that this is not supported. So you can see what is supported here. We have the device object stacks. That's a term related to the layering of devices. In this case, there's just one. It's not layered on top of anything. There's nothing layered on top of that. It's just the only one here in its device stack or device node. These are the terms typically used. And of course, the device object has an address. So given that information, we can look deeper if we wanted to by examining the actual data structures within the kernel. So if I have this driver object, I can go ahead and use the normal DT command to look at, the driver object structure just by typing _driver object and then attaching to it the address of this particular driver object. And you'll be able to see here that we have the name here, driver beep, which is stored as a Unicode string here in this driver name member. And of course, we have the major function array that has 28 entries. So we can go ahead and even open that up and see all these functions shown in a different way, not by the high-level drvobj command, but by looking directly into this array. So you can see here the actual functions, the function symbols, and of course the addresses. So feel free to disassemble that if you want to look into those functions as well. We can also see here the device object member, which should point to the first device object. And this is the one that's supposed to be the BIP device itself, because there's just one. If I click that, or just go to this address, if I click that, we can see that indeed this is a device object which belongs to the driver BIP driver. And there's a special view here that understands the device object structure in a way that tries to provide more I would say, interesting or easier way of looking at the information, like showing upper devices and lower devices. In this particular case, there are none, but you can also go to the raw view and see the actual data structure as it is defined with its members. You can see here the driver object pointer pointing back. You can also see the next device here is null, indicating there are no more devices in this list. It's just the one device. Let's take a look at a similar command, but this time looking at something more interesting, such as the KBD class driver, which is the kernel class, keyboard class driver. Let's go ahead and use that and give it a few seconds to do its thing. I'm going to pause the recording again so you don't have to watch nothing really happening right now. And we get results here. This time we have 4 device objects, not just one. Let's go back up and see where all things started here. So first we have the driver object for the KBD class driver. Of course, it also needs to be here somewhere, so it must be here. Here's KBD. Let's look at the KBD class. So it is here, it exists. Obviously, it has several devices, although in this case, the connection is not easy to identify. If I look at the device objects here, do I have something like KBD something? Well, maybe we have KBD class 2 and class 20, 21, 3. It's not necessarily clear whether they belong to this driver or not. The only way to know for sure is to look in the kernel debugger. So we have this driver object that has this name, and you can see we have 4 device objects. These are the addresses of these device objects. And we can get more details using the drvobj command, as we did previously, or use, well, actually we did that when I clicked one of those links, or use the dt command. But for now, let's take a look what we have in the KBD class driver itself. So obviously there is some kind of entry point here, and there's something called keyboard add device, which is something referred to as add device function. This is a function pointer from a plug and play perspective that's going to be automatically invoked by the kernel when a new keyboard device enters the system, say by plugging a USB keyboard or some other kind of keyboard. Doesn't really matter, because the KBD class driver is configured in a way as to be a filter, upper filter for all keyboard devices, regardless of the actual manufacturer of those keyboard devices. It's not obvious from what we've seen so far where is that configuration actually, but that's something we might look at in the second part of this video series. Then we see the list of dispatch routines, and just like before, certain operations are implemented but many are not, and this is pretty typical of most drivers. So you can see here the list of implemented operations is larger than the one we saw for the BIP device or the BIP driver, but it's still not super big. So we have create and close, which you'll find that are implemented for most, if not all, drivers, because without this you can't open a handle to the device, which usually doesn't make a lot of sense. But this driver also supports the read operation and supports something called flash buffers, and also device side control, internal device side control, and a few more operations such as cleanup here, and we have power management request and system control, which is WMI, and also plug and play. So this is definitely a richer driver that has more, I would say, functionality. If you look at the device objects, we can see we have a bunch of device stacks here, device nodes. Here we can see layering. So there's a device here that has the silly name 60F, and I'll explain in the next session why we have these sort of silly names. And it has an upper device that has this name, that's KBD HID coming from this driver, but this device in fact is unnamed, which is typical of filter devices or filter drivers really. And so we have another one here, and then we have our keyboard class driver, which is the one we're looking at right now, that has this device object, and this device object is actually named and has this name, keyboard class 21. Looking at the next dev node, we can see another one that has a silly name called 60E here, and then it has these two upper layers. One of them is with a device that is unnamed, that is managed by this driver, KBD HID, the human interface device, and then we have another upper layer which is managed by our KBD class driver we're just looking at. Notice this little arrow here indicating that this is the layer that is relevant to the driver we're looking at right now. So in this case we have just 3 layers, not 4. And you can see some other interesting aspects here, which is the actual registry key that indicates the hardware ID. It's actually the hardware ID of this device. And this has to do with whatever bus it is actually connected to. And the service name actually represents the driver registration, which we'll again might look at in the next video. Here's another one, same idea. We have a device object here that has the name A0000A4, and then we have 2 layers on top of that, 2 devices, one managed by this driver, one managed by the KBD class driver, and yet another one in the same vein. So we have multiple device nodes here, or device tags. And the basic idea is that when you have multiple device nodes, when requests come into this device, even if you're targeting this device, because that's perhaps the name you are aware of, still the IR manager will always pass the request first to the topmost layer, whatever that layer may be. And then this layer can decide whether to pass the request down or do something completely different. So that's an example for KBD class. And of course, we can look at these device objects again by clicking here. If I click a device object address, I get a drvobj command, which provides some more details about the device object itself. But just as before, we can definitely look at the driver object and look at the next devices. This time we should see 4 of them in the list. So let's do that again by looking at the driver object in its natural form, so to speak, using the dt command. We can see here device object, which means this is the first one. And you can see that in this case, there is a lower device here. That's the one that we're looking at. And it's layered on top of this entity, which is another device object. It doesn't have any upper devices on its own because we're at the top layer here. We're looking at KBD class. That's information about the driver. But again, we can look at the raw view to see the entire structure. Here we see next device. This time it's not null. There's another device here. We expect these 4 devices to be part of the same linked list. And again, we see that we have a lower device here that is in this address. That's the address to the device object. We can again move forward as before by looking at the row structure, going to next device. So here's the 3rd device. Again, let's look at the raw data and look at the next device. And this time, this should be the last one. So if you look at the raw device, now the next device is null, indicating that is the end of the list. So we have that linked list as we've seen in the last slide. So this is how drivers and device objects are managed from a kernel perspective. Each one of them is a full-blown kernel object. So it's also possible, if I go back to my driver object, say this one, I can go ahead and give that to the more generic object command to give me more details about that being as an object, just like any other kernel object. So you can see that this is in fact a driver object, and there are 6 pointers to this object somewhere within kernel components, and there are 0 handlers, which is very typical of driver objects, because in fact user mode doesn't have a direct API to open handlers to drivers, and in any case it doesn't really mean that much, because we only open handlers to devices, never directly to drivers. It doesn't really mean anything because we can't really send requests to that, definitely not from user mode. It is kind of possible to do some interesting stuff from kernel mode when we have handlers to drivers, but normally it's about opening handlers to devices. Devices are the communication endpoints. Let's look at another final example here. in terms of the drvobj command, let's look at the NTFS file system driver, which is a fairly complex one. So again, this would take a few seconds. I'm going to pause the recording. Here we go with the output for the NTFS driver. So you notice there are 13 device objects here. This is quite a driver managing many devices. Let's go all the way to the top. So we see here the list of device objects, 13 at this point in time. And you'll notice the major function code is fairly big. So the number of functions which are not implemented is fairly small. And you might expect that to be the case since NTFS is a mighty driver implementing a full-blown file system that actually has a lot of functionality. And only things which are completely out of scope are not implemented. For example, the fact that it's about named pipes. Obviously, NTFS is not about pipes at all, so this request is unlikely to be implemented. And there are some other things that don't really make sense, like mail slots. Internal device control might make sense, but it's not implemented by the NTFS driver. Internal device control is just a device IO control kind of call that can only be invoked from kernel mode. So it's implemented by certain drivers, but NTFS apparently doesn't need it. Another thing here which is kind of special is this idea of fast IO routines. Fast IO is a mechanism used by file systems to perform operations which are not based on normal request by satisfying this request coming from the cache. So they have these callbacks for fast IO, which is something special that only applies to very small set of drivers like NTFS. In this case, we see here all the callbacks related to fast IO. And then we get the device tags, just like we've seen with KBD class. In this case, what you'll find in most cases is these kind of layers. We have two layers here. One of them is NTFS, that would be our NTFS file system driver. And then on top of that sits the filter manager. The filter manager is the Windows provided driver that is used to manage file system mini filters, which is the common way today to write extensions or filtering to file systems. It's a much easier way of doing compared to the old legacy file system filters, which was supported and still supported. In fact, the filter manager itself is a legacy file system filter. So you'll find that the filter manager attaches to all file systems, including NTFS, as you can see here. Here we also see something kind of unique. We see another driver called livekd that has a device that is attached here to this particular node. And livekd is a tool from sysinternals that allows us to do live kernel debugging without putting the system into kernel debugging mode. So the way this is happening is by livekd simulating a dump file. So it presents to the debugger a dump file. So the debugger thinks it's a dump file, but actually, in actuality, livekd just grabs information from the live system. And so it is like it actually manages a filter here on top of the file system. So you can see livekd here as well. So that's the basic idea of looking at drivers and devices. Feel free to look at any driver or device that you see. Going to WinObj, by the way, NTFS will not be, you won't see it here under drivers. You'll find that perhaps in a different location. Well, actually, the NTFS, if you try to look for NTFS, you won't find it here, and that's okay. It's actually here under file system. So we have the NTFS driver here. And in general, the drvobj command is smart enough to find it. And if you can't find something, you always use the full find option in WinObj. You can go ahead and click this button and then look for anything you want, and it will look in all the directories until it will find anything that has this particular name there within the system. So there's a driver called NTFS. In fact, there's a device that has a name NTFS, and there's a symbolic link that also is called NTFS. In the next video, we'll see how to open handles to devices and talk to devices based on information that we've seen here and some other details which I haven't yet discussed. See you in the next video.